So this integral, if f is equal to 1, for example. By the way, there is notation for this, which let's call it ds. So then if f is 1, f ds is just the integral of ds. This is just the length, arc length of C, which of course is something which we discussed before. What we're doing now is we are generalizing that definition of the arc length by allowing an arbitrary function instead of 1. And this is something which is useful because let's suppose that you have a wire, a thin wire in the shape of this curve. And let's suppose you want to find the mass of this wire. Okay? So mass of the wire is a funny thing? Well, okay. I guess it was something else which we need. So we want to find mass of this wire. Now, but if the wire, if it is homogeneous, that's going to be the same as the length, or it's going to be proportional to the length of some coefficient. But suppose that it's heavier on this side and it's lighter on this side, so it's not homogeneous. So what you have is a density function. This is very similar to when we discussed masses of two-dimensional, three-dimensional objects. So you're dealing with some density function, and that will be your function f. And to compute the total mass, you have to integrate this function f with respect to this ds, with respect to this measure. In mathematics, this kind of object called measures. What I'm trying to explain to you is that the structure of this integral, of this line integrals, the basic structure of this integral is as follows. It's always, the integrand is always a product, it can be thought of as a product of something which is external, like density, mass density, or vector field, and something which is internal, something which is intrinsic to that curve, and something which has to do with the measurements along the curve. It could be the length of the projection onto the x-axis, it could be the length of the projection onto the y-axis, or it could be the length itself. Each time you get a particular integral. Okay? So these are the two types of integral. I know that it is a little bit confusing because it looks like you have two different things, and especially if you read in the book, I think it's very confusing. So what I was trying to explain to you is why there is such a variety of integrals, and what is the relation between them. Okay? Questions? Right. That's right. So, in other words, what you're saying is, see, you can observe the analogy between the following terms: e dx, q dy, or f ds. Right. So you have the three different types of quantities which you're allowed to integrate. Right. And the first factor here is something which is external. It has to do with vector field or function, like mass density function of the wire and things like that. Right. The second one is intrinsic to the curve itself. It has to do with measuring things along this curve. Here you measure something along the x direction. Here you measure something along the y direction. Here you just take the length of this little piece for each piece. And these are not all possible ways because, well, this is in some sense this is the most intrinsic one because the length is the length. Right. It doesn't know about coordinates. This is already a little bit arbitrary because we have chosen a particular coordinate system. And as we know, there are many coordinate systems, and there's no preferred one. Right. Because for example, I could rotate the x and y coordinate system, so that's already a new coordinate system. And we've learned to appreciate other coordinate systems, for example, limited double integrals. Amongst the coordinate systems we know is the polar coordinate system. So in fact, you could also have expressions like PDR or Q d theta. That's also allowed. You see. And each time you have such an integral, the way you compute it is you parameterize your curve and you reduce the integral to the integral over a line segment on the auxiliary t line. Right. So in the case of a line integral of a vector field, you end up with this integral, right? And in the case of the second type of integral, you end up with this type of integral. But in both cases, you get an integral just along the line segment on the t line. Okay. So this was to explain the different types of integrals because I know that this is something which drives people crazy because the way it's explained in the book, I think, is not really how should I say? There's not enough motivation given. And so what I try to do is to motivate them and explain the difference. But I have to say that we mostly will be interested in line integrals of vector fields, not integrals of functions so much with respect to the measure ds, but line integrals of vector fields. This will be our main concern. And here now we will talk about the first example of a kind of fundamental theorem of calculus applied to this type of integrals. Okay. So to explain this, I have to introduce a particular kind of vector field, which is actually something we've learned before. So let's remember the notion of gradient, right? Gradient. So if you have a function. Again, I work on the plane, so it's a function of two variables. We can take partial derivatives of this function. We have f sub x and f sub y, and we can put them together in what we call the gradient vector. Right, this is a gradient vector. When we studied the gradient, we talked about a gradient attached to a particular point, xy. So it would be a particular point xy, and we would evaluate the gradient. So we have a vector for that particular point. So it's kind of a static object. It was attached to a particular point. But if you look at this formula, it looks like actually we have a vector value function. We actually have a vector attached to each point. So this is precisely the kind of thing that we now call a vector field. So we can now look at the gradient and recognize that the gradient of a function is actually a vector field. This is a vector field. Why? Because at each point you have a vector. At each point xy you have a vector, namely the vector combining the two partial derivatives of this function at this point. And such vector fields are called conservative. And conservative here is not meant to be like a conservative liberal, but it's due to a different etymology of the word. Conservative because it conserves something. It has to do with conservation, which is something we'll talk about later. So this is called conservative. Easy to remember. Now at Berkeley we don't like conservative things, right? But these vector fields are good, so no problem. So what can we say about line integrals of conservative vector fields? So this will be the main subject of the rest of this lecture. It turns out that for such vector fields we actually have an analog of the fundamental theorem of calculus, of the one variable calculus, which looks as follows. So I keep the same picture. I have my curve C, and I consider a line integral of a vector field. It's just that now my vector field is going to be the gradient vector field, or conservative vector field. It is a gradient of a function f. And what can we learn about line integrals of such vector fields? So it turns out that we have the following beautiful formula. So on the left-hand side, we have just a line integral of this vector field over this curve. And on the right-hand side, we just evaluate this function at the endpoints. Okay? So you see, this is the first type of results that I promised last time. I promised last time that we will have results of the following nature. On the left-hand side, we'll have an integral over some domain D, of something which is a derivative of another object. And on the right-hand side, we'll have an integral over the boundary of this domain of that object itself. And so you see, in this particular case, perhaps I should explain that this is point A, and this is point B. So in this particular case, your domain D is this curve. And the boundary of this domain consists of 2 points, B and A. So indeed, on the left, we get an integral over C. And on the right, we just get the values at the 2 endpoints. This is the boundary. Right? This is the boundary. So what is omega here? Omega is, in this particular case, is just our function f. So this integral just means evaluating this function f at point B minus value point A. No question. Shouldn't be a double integral on the left-hand side. Well, I'm sorry? Here. Right. So the question is whether we should put some double integrals on the right. But see, this is a very schematic form, so I'm not keeping track of how many integration signs. In fact, well, up to now, we have an agreement that if it's a double integral, we put 2 integral signs. If it's a triple integral, we put 3 integral signs. But in general, you can just say all of them are integrals, right? So we will know what kind of integral it is by looking at the domain of integrations, the 2-dimensional, 3-dimensional, 1-dimensional, right? So this is schematic, but you're right. To be consistent with the old notation, the number of integration signs on the left would have to be greater by 1 than the number of integration signs on the right. So maybe this minus 1 or something. I don't know. The number minus 1, and here will be a certain number of integration signs. Right? But in this particular case, we do have a single integral on the left, right? Because it's an integral over the curve. And on the right, we have an integral over 0-dimensional object. And usually, integral over 0-dimensional object, we never use the integration sign for that. There will be 0 integration signs because it's a 0-dimensional object. And the integration over 0-dimensional set is just evaluating your function at the points of that set. With signs, though. So it's important which signs we are taking. And let me explain that. That's actually a very important point. You see, when I parameterize my curve, this gives it orientation. Because when I identify this curve with this line segment, I'm using, on this line segment, I have a natural orientation. I'm going from lower value to higher value, from lower to greater value. Right? So here A is smaller, A is less than B, of course, because I write it like this. So when I identify my curve, C, with that line interval, this also, it allows me to move the orientation to the curve. In other words, the curve inherits the orientation of that interval, which if this point corresponds to this and this point corresponds to that, the orientation would be like this. But if it was the other way around, the orientation would be in the opposite direction. So in this equation, we're taking the curve oriented from A to B. So it goes like this, from A to B. And on the right-hand side, we take the endpoint, evaluate the function at that point, minus the value at the initial point. So it has to be consistent. Because if it's not consistent, you will get an equation with the wrong sign. You'll have an overall sign. Okay? Yes? What does f stand for? This one. It was on this board, but I have closed it. F is a function. F of x, y. What is the big F? There is no big F here. Right? Okay. So the question is, we see big F there, but we see big F here, but we don't see big F there, right? So this is what I explained. I said, this is the most general line integral. We take the most general vector field, and we take the line integral. Amongst all vector fields, there are special ones, which are called conservative. A vector field F is called conservative if it can be written as nabla F, as a gradient of some function. Not all vector fields are like this. But from now on, or at this moment, we focus just on this conservative vector fields which have this shape, nabla F. In this case, the line integral will look like this, because the vector field is nabla F, so we just put this nabla F in the formula, so that's the line integral. The statement of this theorem, which is called a theorem about fundamental theorem for line integrals. Line integrals is that in this particular case, the line integral of this vector field can be written in a much simpler way. It's just the difference of the values of the function at the endpoints. You see? So this is, first of all, I want to say that this is a natural generalization of the fundamental theorem of calculus, which we learn for functions in one variable. Yes?
So does that say the path that you go on the arc of the pattern?
Very, very good. So the question is, does it mean that the path going from A to B doesn't really matter? And this is absolutely correct. And this is one of the most important corollaries of this. Because on the left-hand side, it looks like the integral depends on the choice of the path. We could go like this, or we could go like this, or we could go like this, or maybe just take the most boring one, just a straight line, right? But on the right, nothing uses the shape of the curve, only the endpoints. So this formula immediately tells us that actually this line integral, which a priori depends on the choice of the path C, actually does not, only depends on the endpoints. And that's one of the beautiful things about it, which you don't see, without really analyzing this in detail, we won't be able to see that. So it's a first sort of surprising fact about line integrals. And I'm getting to it in a moment. But before I get to this, I want to compare this formula to the formula which we started with last time, which is the fundamental theorem of calculus for functions in one variable, which is that if you have a function in one variable, then we have the formula like this, where you integrate over line segment from A to B, and that's f of B minus f of A. So you see there's a clear connection between the two formulas, there's a clear analogy between the two formulas. In both cases, on the left, we have a single integral of something which is a derivative. Here's a function in one variable, so there's only one derivative. Here, we have a function in two variables, so there isn't a single derivative, but there is a gradient. And what we can do is we can take the line integral of the gradient vector field. And on the right-hand side, it's exactly the same. It's just evaluating at the endpoints and taking the difference. So in fact, this is a special case of this more general formula. This is a special case. We have now generalized the fundamental theorem of one-dimensional calculus to the case of line integrals over arbitrary curves. Okay? Now, let's look at this in more detail, and let's try to figure out some consequences of this. What is this good for? And the first consequence is the one which has already been observed, is the independence of the line integral of the path, which is really striking if you think about it. Because earlier today, I wrote some formula for line integral, right? some specific example. And this example, it was sort of a painstaking process because I had to first of all parameterize my curve, right? Then I had to express my vector field in terms of this parameterization. Then I had to take the derivatives of x and y. And I had to put all this together and finally integrate, right? So it's a lot of work. But now what this formula is telling me is that instead of doing all of that, instead of going through this complicated process, what I could do is just take some function f, so that the result is just the difference between the values of this function and the inputs. You see? So this is a really striking fact. It's a shortcut. It is a shortcut. So now you're happy. Okay, so everybody's happy when things become easier, I guess. But you know, sometimes to get things easier, you have to first make things more complicated to make them easier, right? So I think it was, I forgot who it was who said that. It was a physicist. I think it was Edward Teller who said, what is your goal in life? And he said, my goal in life is to make complicated things easier and easy things complicated. So in a sense, that's not necessarily my goal in this class. But I agree that this is certainly simplification. The right-hand side, we'll all agree that the right-hand side is much simpler than the left-hand side, right? But there is a caveat. There's a caveat to this, because this does not apply to all vector fields. This only applies to vector fields which are conservative. So if your vector field is not conservative, you're out of luck. There's no simplification. You have to go through this process. You see, but there's a huge class of vector fields to which this applies. And now we will discuss to which vector field, how to find out, how to see whether your vector field is a good one or it allows for such a simplification. Okay. But before I do that, I would like to derive the consequences of this, or it's called corollaries. So corollary 1 is that if f is conservative, if f is a conservative vector field, which is not so is conservative. Let's just say is conservative. When I say it's conservative, it means that there is some function f small such that f is equal to nabla of that function, the gradient of that function. Then the line integral of this vector field is independent of the curve. Depends only on the endpoints. On the endpoints. In other words, this is equal to the integral over a different curve of any other curve, provided that that other curve has the same endpoints. What I mean by this, of course, is just what I have already drawn here, but let me draw it one more time. So let's say you have this has two endpoints, but so does this, and so on. I don't want to leave the blackboard, but I could walk all over this classroom and then go outside and the Sproul Plaza and come back. And as long as I start here and come back here, the line integral, no matter how complicated it would be to calculate, the result would be the same. You see, so this is really striking. This is a really striking fact, which enables us. If the question on the test would be calculate over this curve, it looks complicated, but you know right away that instead you could calculate, say, over the straight line, which is much easier. You see, so this really allows for great simplification. Another way to phrase this, is the following. Again, we'll be under the assumption that f is a conservative vector field. That if you integrate over a closed curve is one which does not have endpoints, which does not have a boundary. I'll draw it like this. So this is called, we'll call such a curve a closed curve. A closed curve does not have a boundary. We talked about this last time, like a circle, for example. Its boundary is empty. Okay, so if you integrate over this, you will always get 0. So in this case, you don't even need to choose a simplest path. You just know that you get 0. How to see that? Well, let's pick a point here. Okay? So you can think of this point, you can think of this curve as a curve with a boundary. But in its boundary, this one point appears in two different ways. First of all, it appears as the initial point, something that I have previously called A. But second of all, the same point appears also as the end point, which I previously called B. Right? This one and the same point. If you do this integral according to the fundamental theorem for line integrals, and we are allowed to do this because I'm under the assumption that my vector field is the gradient of a function, then we know that this integral is equal to the difference between the values at the point B and point A. But points B and A are the same in this case. So when I take the difference, I get 0, you see? So this is equal to, this is explanation, f of B minus f of A is 0, right? Because it's the same point. So, in fact, these two statements are equivalent to each other for the following reason. If you have two paths, you see, in this statement, which I call corollary 1, the emphasis is on the fact that if you have two curves connecting two points, connecting the same points, then the answer is the same, right? But if I suppose I know that for any closed curve, the integral is 0, right? This is also implied. This fact will be implied. Why? Because let me draw it on a separate board. So suppose I already know that the integral over any closed curve of f g r is 0.